Hi guys, let's start. So this whole video series will be on financial time series. I'll be covering everything from very scratch, starting from what do you mean by time series, what is stationarity, what is non-stationarity, what are different statistical tests used to check for stationarity for a time series, how to convert a non-stationary data to a stationary data, what is ARMA, Aremax model, followed by how to test for how to evaluate different models, how to how to check if should we take AR2 or AR1 or AR5. So we'll be covering ACF and PSF. So in this video series, we'll be covering all this stuff just to make sure you understand from very basics to very deep. So, so I'll be asking various questions. If you know, just raise your hand. Otherwise, I'll just give you the definition. So let's start with financial time series. So let's understand what is a time series. Okay. Okay. Let's understand. Yeah. Yeah. Okay. Perfect. So let's understand what is a time series first. Okay. So time series, anything, any, any, any variable which has time associated with it. Okay, is called time series. Okay, this is like in very simple words. Let's say we know that stock prices, right? We can have stock prices at time t, which is as of today, t minus one, t minus two, t minus three. So that's why we say stock prices are time series, right? Similarly, if we see, let's say, housing price index, which is an economic parameter. So the value of housing price index changes every month. So this month it can be X, uh, you know, T minus one month, T minus two, T minus three. So there will be different values of HPI, right? So any variable which is this, right, which has any value associated with the time is called time series. I hope that is clear. So so the question is, why do we do time series analysis? Okay, why do we do time series analysis? Okay, why do we analyze any time series data? Is the question. See, the answer to that is time series. We Why we analyze time series in order to extract meaningful insights, or let's say meaningful statistics and other characteristics of the data. So we perform time series analysis. Okay, to extract meaningful statistics. Okay, and characteristics from the data. Also, time series analysis helps to identify pattern and trend, right? Pattern and trend in the historical data, right? So these are, some common reason why do we perform the analysis and what will happen. See, when we are able to understand, meaningful statistics, characteristics of the data, identify trend, pattern. So this can help us in decision making, and that is the core reason why we use time series analysis. Now, this decision making can be into risk management. Okay, you'll see using time series analysis into trading strategies, right? or some other kind of investment, other investments, right? There can be multiple use cases. So now let's understand what are the components of time series analysis. Okay, what are the components? I hope like time series. I hope you are able to understand. So what is time series? Any variable that has any value, let's say any value attached to a time is called a time series analysis. So let's understand the components of time series analysis. So instead of writing time series analysis, I'll just use TSA. Okay. So there are four components, which is trend, cyclical variation, then seasonality, and the last is irregular or random variation. Okay. These are the four components of time series analysis. Okay. So let's understand each and every component. See, what is trend? So let's understand what is trend. Okay. So basically, trend refers to the long-term direction of the series. Okay. Trend refers to long-term direction of the series. Okay. So what does long-term direction mean? So basically, if you see, we have this, right? So trend it can be an upward trend, right? Or it can be a downward trend. So this is what a trend is. So if you see some variables, it will if you see some stocks, right? They grow with time. So that's why you'll see an upward trend in the time series of the stock, right? So this is the first component. Second component, which is cyclical variation. What do you mean by cyclical variation? So basically, cyclical variation refers to the fluctuation in the time series, to the fluctuation in the time series that occurs over time. Okay. Example of cyclical variation is economic cycles or business cycle, right? Example of how so I'm just taking this example, okay, and I'll be moving forward with the uptrend. So let's say we have a uptrend, something like this, okay. So a cyclical variation will be what? Something like this. Okay. So this, so basically here, if you see, this is what? This is trend, and if you see the up and down movement, this is called the cyclical variation. This is the second component. Let's see the third component, okay, which is seasonality. What do you mean by seasonality, right? Seasonality refers to regular pattern that repeat over fixed interval of time. Okay. Seasonality refers to regular pattern that repeats over fixed interval of time. Okay. So seasonality, okay, can be daily, weekly, monthly, or yearly. Okay. Example of seasonality. Okay. So if you see, continuing with the same example, okay. So we have this uptrend. So now we'll add. So if you remember, okay, if you remember, this was our cyclical variation, right? Now, if we add seasonality in this, right? If we add seasonality, so it will become something like this, okay? Something like this. I hope it's clear. Let me. So the this will become the seasonality in this. Okay. Again, another example of seasonality is you'll see during winters, right? The sales of winter clothes, right, will be high. Like if you see, jackets, gloves, earmugs, sweaters, etc., right? So if you see during the winter season, the sales of these all clothes will be high. Why? Because it's a seasonality effect. So sometimes, even in some time series data, you will see a seasonality effect. And the last component, which is irregular variation or random variation. Okay. See, sometimes what happen is you do not some variations happens in the time series which you don't think of, right? So let's say if you see COVID, right? COVID happened. So that is a irregular variation in the time series. So we have a trend, then we have cyclical variation. Now I have added in this I have added let me add seasonality. But what if, right? Just assume, okay, let me complete the seasonality, okay? But now let's assume this. Okay. What if you have a irregular fluctuation in this data? That is, what if something like this happens? Instead of going down, it goes like this, right? So this is called as irregular variation. You expected it to go down, but it remained constant or it went up, something like that. So this is what we say as irregular variation. Something which you don't expect. Okay. So the definition of this will be irregular variation, okay, refers to unpredictable or random fluctuation in the time series that cannot be explained by the other three components, okay? That cannot be explained by other three components. Which are the three components? Trend, cyclical variation, and seasonality. So if something is, coming other than these three, then you can say that is a irregular or let's say random fluctuation. I hope that is clear. So if you have any doubt, please do post that in the chat. Yeah, if you have any doubt, please feel to post. If you are not able to understand anything, add your questions in the chat. Okay. So, a very common interview question. I'll also tell you the interview questions, A very common interview question is, what is a time series analysis, or let's say what is time series and what are the components of time series? So as I said, time series is nothing but any variable that has a value attached to the time. It is called time series, and there are four components, that is trend, cyclical variation, seasonality, and irregular or random fluctuations, right? So this is one interview question. So sometimes interviewer will also ask what is stationarity? What do you mean by stationarity of time series analysis? Or let's say what is stationarity of time series? Okay. See, always remember, if something is stationarity, it will always follow these three rules. That is, it has constant mean. Second is it has constant variance, and the last thing is it has constant, or let's say you can also say it has no autocorrelation. Okay, so if any time series, okay, if any time series satisfies the above three criteria, okay, the above three criteria, it is said that the time series is stationarity. Okay, I hope you understand. So, if any time series has constant mean, constant variance, and constant autocorrelation, then you can say that the time series is stationarity. Okay, so what does what do you mean by constant? I'll give you certain examples just to understand what does a stationarity time series look like and what does a non-stationarity time series look like. Okay, so the question is, what is non-stationary time series first? Okay, non-stationary time series. So if any of the above three rules are violated, then you will say that the time series is non-stationary. Time series is non-stationary. Okay. So which means if let's say the variance is not constant, then in this case time series is non-stationary. Or let's say mean is not constant, rest two are constant. Mean is not constant. Then you'll say time series is non-stationary. So I hope this is clear. Okay, let's understand with graphical representation of what does the stationary time series look like. Okay, graphical or visual. It will be a visual. Okay, graphical. Right. Graphical representation of stationary time series. Okay, so let's say we have something like this. Okay, let's say we have something like this. Okay, so when you calculate the mean of this whole time series, right, you'll see that it has a constant mean. If you see the variance, right, the variance is within the limit, right? It will follow some limit, right? Okay. So variance will be also constant. And when you say constant autocorrelation, what does this mean? Constant autocorrelation basically means that let's say if you have a time series, right? So let's say this is yt, or let's say yeah, this is t plus one, t plus two, this is t minus one, right? So constant or no autocorrelation basically means that this should not have any correlation with this, or let's say this should not this this value should not have any correlation on this value should not have any correlation on this. This is what we say as constant or no autocorrelation. We say as this as no autocorrelation. So basically, why do we say that? Why do we say it should not have autocorrelation? The main reason is if let's say these two have autocorrelation, right? So if let's say between these two time points, if there is any error, so the error will fluctuate over the time, right? So the error will fluctuate in this time, in this time, in this time, in this time. So what will happen if let's say you are building a time series model, right? So this is your let's say this is your actual values and these are your predicted values, right? Let's say this is the actual and this is your predicted. So if you see the error between the error, this is the error, right? The error between the actual and the predicted will grow. That's why we say there should be no autocorrelation. Okay. So this is an example of stationary time series. Now, what does a non-stationary time series look like? Let's say if you have any time series like this. Okay. So if you see, okay, let me give you a better example. Yeah. So non-stationary time series. Okay. So if you have something like this, right? So this is a perfect example of non-stationary time series. Why? Because when you will calculate mean, it will not remain constant. When we'll calculate variance, you see the limits are just going up and down. And even when you will calculate autocorrelation, there will be some correlation between the time values. So how will you understand if all these values, if it has a constant mean, constant variance, or no autocorrelation? How will you understand, right? Don't worry. I'll give you. There are a lot of statistical tests which can be used, which basically tells if the time series has mean, variance, autocorrelation or not. Basically, if the time series is stationary or not, right? So just give me 1 second, yeah. So yeah. So let's move on to next topic, which is what is a unit root test? Any idea? Like what do we understand? What do you guys understand by unit root test and time series? Anyone who knows this concept? Unit root testing and time series. Let's understand. Okay, I see no hands, so I'll move. Okay, let's understand. Unit root test. Okay, so unit root test is basically a statistical test which is used to determine whether a time series is stationary or not. So basically, a unit root is a characteristics of a non-stationary time series. So when I say that this time series, let's say unit, basically if you see like the time series has unit root, we'll say that the time series is non-stationary. So as simple as that. Okay. So unit root test is a statistical test which is used in time series to determine whether the series is stationary or non-stationary. Okay. Stationary or non-stationary. So this is the first thing. Second thing is a unit root. Now we are saying just saying unit root, not the unit root test. Okay. A unit root is a characteristic of a non-stationary time series. Okay. As a non-stationary. So a unit root is a characteristic of a non-stationary time series. Geet, I saw your question. Let me take that question after I explain this concept. So basically, yeah, a unit root is a characteristic of a non-stationary time series. Okay. So what do you mean by this? Basically, it means that unit root will, it can either have non-constant mean or non-constant variance, or it can have autocorrelation. Okay. So this is what you mean by unit root. So unit root test is basically a statistical test, which is used to understand whether a time series is stationary or non-stationary. And only unit root, right? Unit root is a characteristic of a non-stationary time series. So just remember this, and I guess you'll be great. Um, taking the question that Geet asked, in the plot you used for autocorrelation, the variance increases with time, will also make the plot look the way that way, right? Um, so autocorrelation has anything to do with variance. Okay. So let's see if we see this thing, right? Will see sometimes what happens is if you see this plot, right? We know that of course the variance it does not has a constant variance, because if you see this plot you can always see it has a constant variance. But if you see this plot, the variance is going up and down, then constant, right? So you know that the variance is not constant over the time series. And see, sometimes understanding if the times, if the, just by the graphical representation, understanding if the time series has autocorrelation or not, it is little challenging. So that is why tests have been there are several statistical tests that have been developed, which basically helps us understand if the time series has autocorrelation or not. So sometimes, even though let's say you'll see, and I've, practically seen that some time series, they look, they have constant mean, constant variance. But when you actually use the statistical that test, then you realize, oh, this does not have a constant variance. So sometimes, graphical representation is not the best way to check if the time series is stationary or not. But again, will be, this is just, if you just want to, see if the time series is stationary or not, the first stage is this, but again, we will be covering different statistical tests uh, in this video series. So I hope this answers your question. Okay, so let's see what are statistical tests. Okay, what are the statistical tests for times for okay, what are the statistical tests for checking stationarity? Statistical tests for checking stationarity. Okay. There are two common tests that most of the people use. That is augmented Dickey-Fuller test and KPSS test. Yeah, Sujan, you are right. I saw your comment in the chat. So Dickey-Fuller test. Okay, so augmented Dickey-Fuller test, which is also called the ADF test, and the second is KPSS test. Okay. So just to write the spelling of KPSS, it is a bit long, but yeah, I'll still write for you guys. Okay. So this is how we say, but most of the people, because they don't speak the whole name, it's better, we even in the industry we say, oh, it's a KPSS test that we have used. So this is the full form of KPSS. Let's understand both the test, okay? Both are used for checking stationarity of the time series, okay? Let's check the first test, ADF test, which is the augmented Dickey-Fuller test. Okay, so what is this test? Okay, this test is most widely used for checking the stationarity of the time series. Okay, this is used for checking the stationarity of the time series. Okay, so of course we all know this. The statistical test have a null hypothesis. Okay, which we represent as HO, and then we have a alternate hypothesis. Okay, which we represent as a HA. Okay, so in null hypothesis we say that there is a unit root in the time series. Okay. And what do you mean by unit root? It is a characteristic of non-stationary data, which basically, so what I'm trying to say is time series is non-stationary, right? And alternate will be just opposite, which is time series is stationary. Okay. Now we all are good statistical students, so we know that we always try to reject null hypothesis, right? So what are the conditions to reject null hypothesis? Okay. So as we know, we always try to reject null hypothesis. Condition is if p-value is less than 0.05, then we will reject null hypothesis. Okay, which means if this condition is true, this means the time series is stationary. Okay. Also, this is first. Also, you can check if so when you'll do the augmented Dickey-Fuller test in Python, you'll be also getting the t statistic, which is also called the test statistic, t stat, and you will also got the critical value. You will also get the critical value. So if critical value is greater than t statistics, then you will say reject null hypothesis. which basically means this condition is true, which means time series is stationary. Okay, so you can check any of the conditions. Okay, so if critical value is greater than t statistics, or if p value is less than 0.05, you'll say time series is stationarity. So this is the first test, okay, which is the augmented decupular test. Okay, now the second test. You might be thinking, why do we have a second test, right? When we already have one test which is checking for stationarity, why do we need to do the second test? There is a big reason for that. The reason is KPSS test is used to check if the time series is trend stationary. Okay, so KPSS test is used to test if the time series is trend stationary. Okay, so what do you mean by the word trend stationary? You might be thinking. Okay, so trend stationary basically means that the series has a constant mean, constant variance, but it can have a linear trend. Okay, so this is what we say as keep trend stationary. Okay, always remember this is what we say as trend stationary. Okay, now let's look at the null hypothesis and the alternate hypothesis. Here, the null hypothesis is that the time series is trend stationary. Okay, and the alternate is the time series is non-stationary, which basically mean that it has the presence of unit root in the model. Okay, the model. Okay. So in this case, if see this, the way we deal with this specific KPSS test, it's just the opposite. It's just the opposite with the augmented decupular test. And why I'm saying this is, so in this specific case, right? So if here, okay, if the p value is less than 0.05, okay, we say that we say that we reject the null hypothesis, okay, and we say that the time series is, since we are rejecting this, we are accepting this, right, is non-stationary. If you see here, right, if you see the null hypothesis is it is trend stationary, but in ADF, right, what we were assuming is it is non-stationary. So that's why I'm saying it's just the opposite, right? So in this case, okay, so in ADF, okay, we are saying this is time series is non-stationary. Alternative, time series is stationary. Whereas in KPSS, we say we say null hypothesis that the time series non is time or trend stationary, and alternative it is non-stationary. So in this case, if p value is less than 0.05, right, then what do we want in this case, right? We want p value should be less than 0.05. That is how we'll get that our time series is stationary. In this case, we want p value to be greater than 0.05, and that is how we'll get time series is trend stationary. So I hope you understand this thing, right? Why do we want? Because we have, if you see, we have just flipped the hypothesis, right? And that is why this. So that is why we this thing. Okay. So I hope you understand the difference between null hypothesis. I mean the augmented decupular test and the KPSS test. I'll just wait for some few minutes. Do you guys have any doubts on this? Okay, so I'll be moving forward. Okay. Now, what is the difference between trend stationary and different stationary? Okay, let's understand in detail. Okay, this is okay. I see some doubt. Yeah, sure. Unmute yourself.
Hey, hi. Um, so are you gonna talk about why we are
Hello.
spending so much time talking about stationary and non-stationary, as in why they are important?
Geet, your voice is not audible properly. Can you say that again? Maybe can you come close to the speaker?
Yeah, maybe now. Better?
Yeah, yeah, better.
Sorry about that. So are you gonna talk about why we are spending, like since you're spending so much time on stationary and non-stationary, I'm guessing
Mm-hmm.
they are important somehow. So
Right.
are you gonna talk about why, they are important or why we are talking about
Um,
them?
def Definitely. See, when you are building, I can speak for some minutes because we have a lot to cover. But
Okay,
and I can we can also connect offline on this. See, but
sure.
why do we check for stationarity in any time series? Why this whole concept of stationarity and time series is important? I feel it's very important because when you are building any time series model, if let's say your data is non-stationary, which basically means that let's say if your data has autocorrelation between them, or if your data has let's say a lot of variances, and or let's say the mean is not constant, right? So when you build the model, right, and let's say you have trained your model on 10 years of data, which is like a non-stationary data, and as soon as you go and predict the future from that specific model, it will be really bad. The prediction will be way far from your actual value. So that's why we always prefer, to convert all the non, all the uh, all this data, all this non-stationary data into stationary data. Even if you see stocks, the first thing that you do in stocks is you take the log return, right? You never
Mhm.
model stock prices. You always try to kind of first convert the stocks into returns, and then you model returns, right? Well, what's
Yeah,
the main reason? When you take, when as soon as you take, as soon as you take this log return, that's how you convert a non-stationary data into stationary. So that
nice,
is the main reason of, converting. That is why this whole concept of stationarity is important.
nice. Nice. Can I ask one more question? Um,
Yeah, sure.
so I'm just confused about how we can have constant mean, but the trend stationary is a linear trend. Because can you like show a plot where,
So let's say
yeah,
you have trend. Let's say you have trend like this, okay? And
uh-huh,
if you're if you're um if you're this is moving, okay, I'll don't worry, I'll just cover this question. Just let me finish it, and I can come back on
sure,
this,
I
okay?
can, yeah, I can
Okay.
answer later. Thank you. Yeah.
Yeah. Yeah. So let's understand what's the difference between trend stationary and different stationary, okay? So I know, guys, this few concepts will be, if you're reading for the first time, it might sound, why we are doing this, but just hang on in this session, and I can take all your doubts. Trend stationary and different stationary, okay? So what do we mean by trend stationary or different stationary, okay? So different stationary. First, let's say different stationary, okay? Different stationary is created by taking the difference between consecutive observation in a time series. Okay, in a time series. So when you take a consecutive difference, when you take the difference between the consecutive observation, what will happen? So it will have constant mean, constant variance over time. Okay, and also if there's any trend, the trend will be removed. Okay. So if you have your data something like this, okay, let's say yt minus 1, yt minus 2, yt minus 3, yt minus 4. So if you do this, if you take the, let's say, if you take the difference between these, right, in the resultant time series, right, whatever you'll get will have will have these properties of stationarity. So this is what we say as difference stationary. Trend stationary, what does this mean? It basically means that it has constant mean variance over time, but has a changing trend, right? So it can have both upward or downward trend, okay? But the fluctuation around that trend are consistent, okay? So let's say, um, okay. So I hope trend stationary I already covered here, right? I'll also just write here. What is trend stationary? Okay. Trend stationary means it has constant mean, constant variance, but has trend associated with it. Okay. So it can be either the trend can be either upward or downward as we revised in the in the start of the session. But always remember, but the fluctuation around the trend will remain consistent. So since we have two tests, right, ADF and KPSS. So let's say there'll be four conditions, okay? If let's say this test says that time series is stationarity, this says the time series is stationarity, right? Result is that the time series is stationarity. If this test says the time series non-stationary, this says the time series is non-stationary, the end result is time series is non-stationary. Okay. Now let's say ADF says the time series is non-stationary and KPSS says time series is stationary. Then this means that the time series is trend stationary. Okay. Now if let's say ADF says the time series stationarity and whereas KPSS say the time series non-stationary, right? This can be also the case, right? So this means that the time series is different stationary. Okay. So I hope you understand this concept. Okay. I hope did you guys understand this concept? Like, see, these two are simple, right? Because if both are saying, if both are saying stationarity, then of course stationarity. If both are saying non-stationarity, of course it is non-stationarity. If one is saying non-stationarity, just as why do think why will ADF say it is non-stationary whereas KPS says it will stationary? Because KPS know that the time series is trend stationary. So if you give a trend stationary line to a trend stationary data to ADF, it will of course say non-stationary. But if KPS is saying it's stationary, then it means trend stationary. And similarly, if it's different stationary. So let's understand some ways. Okay, let's understand some ways of how to convert non-stationary data into stationary. And also, I'll tell you, most of the recruit hiring managers they only know ADF. I have worked a lot on time series modeling. That's why I know KVP, like practitioners use KPSS. So if you'll mention KPSS, I'm very sure that the hiring manager will be really impressed. So let's see some of the ways in which we can convert a non-stationary data into stationary. So the first way is of course differencing, right? That is what do you mean by differencing? Basically, you take the difference between consecutive values. Okay, this is the first method. Second method is transformation. What do you mean by transformation? It can be a log transformation. Sometimes people do square root transformation, or even people have used power transformation. It depends what kind of data you have. So, depending on that, you basically use transformation. If you see, most of the time for stocks, we do log transformation. Okay. Third, seasonal adjustment. What do you mean by seasonal adjustment? Okay. So, so seasonal adjustment basically means that, of course, your time series exhibits seasonality. In your time series, there is some seasonal component. So if you remove that seasonality, right, then it can happen that your time series can be stationarity. Similarly, detrending. Detrending basically means that your time series has a trend, and if you remove the trend from your time series, remove trend from your time series, then your non-stationary data will become stationary. So these are four powerful techniques, that most of the practitioners use to convert a non-stationary data into a stationary data. Okay, so moving on to models, right? Let's say moving on to models, we have autoregressive, moving average. These all are time series models. Okay, autoregressive, moving average, ARMA, ERIMA, ERIMAX, SERIMAX. Okay, so let's cover one by one. Okay, so let's start with AR model. So AR, as the name represents, auto regressive. I hope you guys have studied linear regression, right? So from that linear regression, regressive word is there. Auto means self, right? What do you mean by auto? It means self. So auto regressive model is a statistical model used. Okay, it's basically okay. Yeah, it's a statistical model in which the dependent variable is regressed. Regress means linear regression, okay, against its own lagged values. Okay, so it is regressed against its own lagged values. Okay, I hope you understand. So how does AR1 model will look like? Okay, we'll have YT is equal to C plus, let's say, 5 1 y t minus 1. Okay, plus some error epsilon. Okay, so here C is a constant, phi 1 is basically the coefficient, yt minus 1 is basically the lagged value, and et is the error term. In Python, when you do, right, in Python, when you basically run a AR model, it will give you this part and this part. Okay, but when we write in mathematics, we write in this way. So similarly, a AR2 model will be what? Yt is equal to C plus. Now there will be two terms, right? There will be two terms of yt minus 2 plus et. Similarly, AR3 yt is equal to C plus phi 1 yt minus 1, phi 2 yt minus 2 plus phi 3 yt minus 3 plus epsilon t. So now let's generalize it. ARP, okay? We can write this as yt is equal to C plus phi 1 yt minus 1. Till this will go up till phi p yt minus p plus epsilon t. Okay? This is like the generalized equation for an autoregressive model. So here P is what? P is the lag term, okay, that we are considering. Okay, how many lag term we are considering? So in this case, we were considering only two lag term, that is T minus 1, okay, that is T minus 1 and T minus 2. If you see here, the lag term was 1, that is T minus 1, yt minus 1, okay. So as you know, phi 1, phi 2, you see, um, all this phi 1, phi 2 up to phi p, these are nothing but coefficient. of the lag term. Okay. Again, yt minus 1, yt minus 2 up till yt minus p are nothing but the lagged value, okay, of of yt. C is again constant, epsilon is again the error term. Did you guys understand what is an AR model? So it's nothing but we are just regressing, we are just regressing again against the previous value. That's it. So let's see what is a MA model. Okay. See, all the time series model are regression models only. Okay. Don't think is something else. It is just a regression model. So in MA model, okay. So MA model is basically if you see here, MA model is a statistical model. Okay? MA model is a statistical model in which you regress against you regress the dependent variable, which is yt, okay, against the error term, against the past error term or residual. Okay. So let's say, so here, if you remember, AR was denoted by P, right? MA will be denoted by Q. Okay. So when I write MA1, okay, how can I write this mathematically? So MAYT is equal to, because this is always the dependent variable, right? C plus theta 1 ET minus 1, right? ET minus 1 is what? The theta. See, ET minus 1 is the error term. Okay. That's a constant error. Okay. Similarly, this is MA1. Okay. MA2 will be what? There will be two component. C plus theta 1 ET minus 1, theta 2 ET minus 2, and plus some error term. Okay. Right. Some error term. Okay. Similarly, we can say that MA P, that is, we are regressing against the pth order, right? So we can similarly write theta 1 ET minus 1 up till theta p ET minus p plus some error term. Okay, similarly, see, if you do this, I guess if you run if you use time series model in Python, you will see this part only. I will not see the constant, but when we write, it's the way how we write. So So now your question might be, you're like, how will we analyze, should we consider, let's say, AR1 model, AR2 model, or let's say MA1 model or MA2 model, right? You might be thinking, how many lag term we should take, right? How many lag term should we take? So question is, how many lag term, anyone, any idea, should be used in AR or MA model? You guys can unmute if anyone has an idea.
Like all those mm,
Sorry, can you
second,
say that again?
the p values of those models should be less than the significance.
Yeah, that is one way, but yeah, definitely p value is definitely one way. But we again have
Log likelihood.
no, not the log likelihood. Let me tell you. Okay, so we have something like
Yeah, yeah.
ACF and PACF. Okay, ACF we says autocorrelation function, autocorrelation function. PACF is partial autocorrelation function. Okay, so what will happen is basically ACF, right? What is ACF? ACF is used for MA model. Okay. Always remember. This is like the key part of it. What is an ACF? What is autocorrelation function, right? So ACF gives us the values of autocorrelation of any series with its lag term. So what does this mean? This basically means that it will tell you how much a time series is autocorrelated with its previous time lags. Okay. So let's say, so when you plot a ACF of the time series, right, you'll have something like this. You'll get a figure something like this. Okay. So this will be a so you'll have a blue line, then you'll have you'll have you guys seen something like this? Any plots like this? So here you'll have uh, from 0 to 1, and then there will be a blue color, there'll be a blue color line, something like this here. Okay, something like this you will see when you plot a ACF, right? You'll see something like some figure like this. So here, what does it mean? And let's assume this is crossing this line. So what does this mean? Okay, so this blue area, okay, the blue shaded area, which is this, the blue shaded area represents 95% confidence interval above around the correlation coefficient F estimate. So what does this mean? Basically, if we have any point outside this blue area, then it means that that many that many lags we have to consider. Okay. So here in this case, if we see, this is the first point, this is the second point, right? So here you see we have two lags, 2 points that are outside the blue shaded area. That's why we'll say we'll take AR. Okay. This is ACF, right? So we'll take MA2 model for modeling the time series. This is one of the way of understanding how many components or how many lags you should consider in your time series. Okay. Now, similarly, if you see PACF plot, so this we saw ACF plot. PACF plot will be similar. It will be similar. Okay. It will be also the shaded line, but PACF plot is for AR model. Okay. So what does a PACF stands for? It stands for partial autocorrelation. Partial autocorrelation function. Okay. And it measures the correlation between a time series and its lag value after removing the effect of intervening lags. Okay. This is the key component of ACF. Okay. So ACF function, PACF function measures the correlation between a time series and its lagged value after removing the effect of intervening lag. Intervening lag. Okay. So I see a question. Okay. Yeah. So if you see in the chat what Srujan has just posted, right? So that's perfect, right? If you see, that is what we say as ACF and PACF plot. So if you see in the blue shaded area, any lag which is outside the shaded area, we'll say that as will take that much as our lag term. Okay. So if you see 2 points outside the shaded area, we'll take as AR2 or MA2, depending if the chart is ACF or PACF. Okay. So this is just to so ACF Again, just to summarize, ACF is used for MA model, PACF is used for AR model. Okay. Why do we use this? This is used to understand the how many lags do we need to consider. Okay. Okay. I hope you understand this thing. Now let's see ARMA model. Okay. Let's see ARMA model. So ARMA model is nothing but we combine both the AR and the MA model together. Okay. So it is represented by ARMA P, comma Q. P is nothing but AR term, Q is nothing but MA term, right? As we have studied. So so basically this model, what does this model do? We regress against the values as well as against the errors, right? The past values and the past errors. That's why we say this as autoregressive moving average. Okay. So here we regress the dependent variable, right? Which is YT against the past values and past errors. Past value basically means AR component. Past error basically means MA component. Okay. So the mathematical representation of ARMA P comma Q will look like something like this. Okay. YT is equal to C plus, let's say we consider ARMA 1 comma 1. Okay. Let's consider ARMA 1 comma 1. Okay. So phi 1 YT minus 1 plus theta 1 ET minus 1 plus some error term. Okay. Let's see ARMA 2 comma 1, which basically means there are two components of AR and one component of MA, right? So YT is equal to C plus phi 1 YT minus 1, phi 2 YT minus 2, theta 1 ET minus 1 plus some error term, right? So you can generalize this YP is equal to C plus phi 1 YT minus 1 up till phi P YT minus P. Similarly, theta 1 YT minus 1 up till, sorry, theta 1 ET minus 1, because this is the MA component, right? Plus up till theta P ET minus P plus some error term. Okay. So this is what we'll say as ARMA. This part will say as ARMA P comma Q. Okay. I hope you understand this. See, sometimes AR model will work, sometimes MA model will work. It depends. You need to try and test different models just to understand which time series model will work. If you see linear regression model, right? Now we have so many type variants of linear regression like ridge regression, lasso regression, elastic net regression, right? We have linear regression, and so we need to check which regression will work great for the time series data. Similarly, we have different time series model AR, MA, ARIMA, ARIMAX, ARIMAX. So in a similar way, we need to check which model will work great for the data. Now, ARIMA model. Okay. See, ARMA and ARIMA, there's only one difference. If you see, okay, which is this I. This is the only difference. How, so ARIMA model, the name is autoregressive integrated moving average model. This is how we say as this is what we say as ARIMA model. Okay. What does this term integrate mean? Okay. So okay, one more thing. ARIMA is represented by this P D Q, where P is the AR term, D is the differencing term, MA, or let's say PD, Q is the MA term. If you see from top, P is always used for AR, Q is always used for MA. Here we have one extra term which is D. See, D basically means the differencing. as we know, the first order if you see first order differencing, what does this mean? If we have a time series data, right? Something like this. So we'll be doing basically the first order differencing, that is yt minus 1, yt minus 1 minus yt minus 2, and similarly we'll be doing the differencing, right? And the last value will be removed or something like that, right? So, or let's say the first value will be removed depending on how your time series is arranged in ascending or descending order. So this is what we say as first order differencing, that we are you are calculating the difference between this times this data and this data. Similarly, this data and this data. So this is what we say as first order differencing. So if we consider first order differencing, then the value of d will be 1. Now, if you consider second order differencing, the value of d will be 2. What is second order differencing? Let's say yt minus yt minus 1 will gives you, let's say, xt. Similarly, xt minus 1, xt minus 2. Again, you difference it. So this is what we say as second order differencing. Okay, so here, d is equal to 1 means first order differencing, d is equal to second means second order differencing. See, one more thing is, sometimes if you're dealing with AR, MA, see, if you're dealing with AR, MA, IRMA model, right, you need to give a stationary data. Okay, for ARIMA model, right, since we have differencing integrated in it, right? So even if you give a non-stationary data and just put d is equal to 1, it will automatically convert your non-stationary data into stationary data. So when you put d equal to 1, you are saying that apply first order differencing to your time series data. Okay, to your time series data. This is what we, when you say d equal to, so always remember, for a AR, MA, and IRMA model, you have to always give a stationary data. For ARIMA, you can give a non-stationary data, but always remember d is equal to, you have to put d equal to 1. But let's say if you are giving, you have already converted your data. Yeah, if you have already converted your data into, let's say if you have already converted your data into stationary, then just put d equal to 0, which basically means that you are not doing any differencing on the data. So this is what we say as ARIMA model, right? So, okay, so now the difference between ARIMA PDQ versus ARMA P comma Q is what? It's only the differencing term, right? It's only this term, right? That we have the flexibility of converting a non-stationary data into stationary, while in ARMA model you always have to give a stationary data. Okay. So now, moving on, what are uh, some common metrics, right? Let's say, what are some common metrics for evaluating time series models? Okay. Let's say you have trained, you have tested, now there's this actual value, there's this predicted value, right? Let's say this is the actual, this is. So how will you test which model is performing better? Or let's say, what is the evaluation criteria? So we have various evaluation criteria like mean absolute error, mean square error, then we have root mean square error. Okay, then we have mean absolute percentage error. Okay, we have, this is called mean absolute error, mean square error, root mean square error, mean absolute percentage error. Okay, what does this mean? What does mean absolute error or mean square error? What does this mean? Let's say you have this value. Okay, you have your predicted value and you have your actual value. Okay, let's say 10, 9, 11, 10.7, 11.2, 11.1, let's say 7, 6.9, something like this. You have your actual for, and these are your times t minus t plus 1, t plus 2, t plus 3, something like this, okay? So your model has predicted all these values, right? So first thing is, always remember, will for any of these matrices, let's say we see mean square error, will always go from this in the reverse direction, okay? That is from right to left. Will always go in the reverse direction. That is, calculate the error. Okay, just remember this. Will always go in the reverse direction. What is the error? Error is nothing but actual minus predicted value. Okay, so what is 10 minus 9 is 1, 11 minus 10.7 is 0.3, 0.1, 0.1. Okay, so this is your error that you have received in your time series data. Okay, so you have calculated your error. Second is square the error. Let's square. And the third is take a mean. So what will be the mean? Which is um I guess I guess it will be 1.11 1.11 divided by 4 will be the mean square error for this model, right? Whatever the answer is. So always remember, we'll go in the reverse direction. Similarly, if we see root mean square error, right? How we'll go is in the reverse direction. First we'll calculate the error, square it, mean it, root it. So in this case, right, we'll follow the same step, and then what we'll do, the extra step is taking the root, right? So 1.1111 by 4. So we'll take the root, whatever the value, we'll take that as root mean square error. Okay. So most of the time, how I use is I generally use root mean square error and mean square error just to evaluate different models, because I feel those are like some good matrices. It also helps us, like how much I have studied in data science and stuff. People say it of using root mean square error and mean square error. So this is how you evaluate your time series model. I guess uh, there's one last thing which I want to cover, which is like white noise. White noise is like, some people might ask you, some will not. So white noise is basically it's a random signal that has a constant mean and constant variance. Okay, so so characteristics of white noise is it has constant mean and constant variance. Okay, so it is a very important concept in time series analysis because it is used as a benchmark. The white noise is used as a benchmark against other time series model. So what do I mean by that is, see, whenever you use whenever you are working on any time series model, people can say uh, does your model has white noise or something like that? Does your data has white noise? You'll say yes. What does that mean? It basically means it has constant mean and constant variance. Okay. Also, one more thing is white noise. In white noise, there is no correlation. Okay. We say that there is no correlation. Okay. So these are three important concepts. These are three important properties of white noise, that is constant mean, constant variance, and no correlation. Also, I guess in the up that I mentioned here, it will be constant stationarity is constant mean, okay, constant mean, constant variance, and I guess constant. So I guess it should be constant autocorrelation. Yeah. So guys, this was all for today's topic. Let me pause the recording, and I can take all your doubts.